as the head of our Department of Physics, IPB University, to give his speech for 1 or 2 minutes. The time is yours.
Okay, thank you very much, Pak Dodi. Okay, good evening, ladies and gentlemen. Thank you very much for your participation in this event. Yeah, IPB Physics Talk itself is a bi-weekly event organized by the Department of Physics, IPB University. It is a unique and signature event organized by us to expose our society, in this case, the faculty member and student in physics department everywhere, yeah, with the cutting edge and state-of-the-art of physics research and their application. So far, we already have 68 series. And for today, we have the 69th series. We are very honored and happy to have Professor Bartlomiej Czech, yeah, from Institute of Advanced Study, Tsinghua University, as our guest speaker. Thank you very much, Professor Bartek, yeah, for coming here. I know you have a very busy schedule, but still accepting our invitation for today's talk. Yeah, we are very honored to have you here. And for today, as a moderator for this event, Dr. Renat Hendradi Hardinata, aka Pak Dodi. Yeah.
Yes.
And okay, let me start. I don't know, maybe you already learned a little bit about the Indonesian culture. Let me start with pantun. Do you know pantun?
Yes, I know pantun. It rhymes.
Yeah, it's rhyming. Yeah, it's a rhyme sentence. Yeah. Okay, let me start with this rhyme. 100.000 itu cepek. Cukup untuk membeli mie laksa.
Cakep.
Ya, cakep, handsome. Mari kita menyimak uraian Prof. Bartek, bertambah ilmu untuk kemajuan bangsa. Ya, thank you very much.
Okay. Thank you, Professor Tony. Pak Tony.
Pak Dodi, please.
Okay, very nice introduction. And before we start with the speech, the interesting speech, I would like to read about the CV of our dear speaker today. Can you all see the screen in front of me?
Yeah, I can see that.
Yeah, okay. So Professor Bartlomiej Czech is also in the Institute for Advanced Study at Tsinghua University, Beijing, China. And he's born in 1979 in Warsaw, Poland. And he speaks many languages. I think more than 5 languages. Yeah. Maybe after some time also learn Japanese and Sundanese. I don't know. But we are very honored to have you here, and also previous employment, the very famous Institute for Advanced Study. I think he's where Albert Einstein also resided, for some time in Princeton, New Jersey, USA. From 2016 to 2018, also Stanford Institute for Theoretical Physics as a research associate. And before that, also University of Amsterdam and the University of British Columbia in Vancouver, Canada. And has also until 2001 visiting fellow of the Perimeter Institute. I think is also very known in theoretical physics, Perimeter Institute in Ontario, Canada. And he finished his Ph.D. in physics 2009 with the thesis of statistical effect in large and supersymmetrical gauge theories, and also was a graduate from Tata Institute of Fundamental Research and Harvard University for your bachelor degree. Is it correct?
That's all of these things are correct. Yes.
Okay, so Harvard University. I'm curious, where do you meet your wife Stella? In Harvard University?
Oh no, even before that. So I went to an international high school, and this was a very special high school where in 1 year we only had 100 students, but from 80 countries. So on average, every country would send 1 or 2 students at most. And Stella was the representative of Indonesia. She got a scholarship there, and I was the representative of Poland. So we already met sejak zaman SMA.
Yeah,
and then luckily we both got into Harvard, but we were in different years. so we never competed against each other. So I entered Harvard in 1998, and she did in 1999. So
okay. So you were the senior when you were in high school. So one
no,
year.
we were in different years. I was 1 year above her, and
Okay.
so I applied for. I was 1 year her senior in high school, and also I applied to Harvard 1 year earlier, and that's.
And then she followed you to Harvard. Yeah.
And then she managed to, yes. So this was a little miracle that we both got in there.
Okay. So I think there is a lot of motivation behind. Yeah. So I think that's the most interesting part of your CV is how you meet your.
I see.
Okay.
Itu
So just joking.
sudah takdir.
Sudah takdir ya. Okay. Pak Tony is smiling ya. Okay. Yeah, I think I don't have to read all, but you can see a lot of publication and also in very famous journals, Journal of High Energy Physics, yeah, and mostly about holographic entropy, also entanglement. So some of the topics, I think you will put together some of your publication into this talk today, right? And also, yeah, mostly in physical review, yeah, journal high energy physics, cage theory, and so on. I think we can find in internet all your details, and also yeah, in physical review letters, in 2018 Einstein equation from varying converse. Yeah, there are many more publication, but let's just hear the talk that we wait for so long, yeah, before the plane takes off. Okay. So Prof. Bartek, the time is yours, and please, you have yeah, you can have 30 minutes or more.
Did you say 30 minutes?
Yeah,
Like
it's flexible. Yeah.
Oh, okay. Okay.
It's
So,
up to you. 45, 1 hour, as long as you don't miss your airplane.
Okay. Thank you very much. So first of all,
you can stop
thank you.
any time.
So first of all, thank you very much for this kind invitation to Prof. Tony, Prof. Hendradi, Prof. Dodi, and all the others who kindly extended this invitation to me. So I am, yes, and it's I am saddened that I couldn't be there in person, and I thought I could be there in person. So this is a disappointment for me. Beautiful city of Bogor. I have never seen Rafflesia Arnoldi, so I thought maybe I could see it, but it didn't happen this time. Maybe next time. So this talk is about work that I mean, you have seen the title of it. This work is, but I should talk first about the context for this work, and maybe most of my talk will be really about the context. So this is a talk about the ADS-CFT correspondence. And the ADS-CFT correspondence is a duality which relates quantum gravity in special boundary conditions called the anti-de Sitter boundary conditions, and a special type of field theory called conformal field theory. Now, maybe what is anti-de Sitter gravity, or gravity with anti-de Sitter boundary conditions? There are several ways to think about it. One way to think about it is that if you when we learn geometry and differential geometry or maybe general relativity, then we first learn about curvature and distinguish manifolds that have positive curvature or zero curvature or negative curvature. So an example of a surface that has positive curvature is the sphere, like the surface of the Earth, yes? The surface of the Earth by itself has positive curvature. And one way that you can tell that you have positive curvature is that if you draw a perfect, I mean, not a perfect, just some triangle on the surface of the Earth, yes, then the sum of the angles inside it will be more than 180 degrees. On a flat surface, it is precisely equal to 180 degrees. Like imagine on the surface of the Earth, a triangle which is made by the equator, yes, I know even that word, katulistiwa, right? And two different meridians. That's a perfect, I mean, that's a good triangle on the surface of the Earth. And but already the equator with the meridian makes 90 degrees. So it's 90 degrees, 90 degrees, and some extra on top at the North Pole. at Kutub Utara, for example. And so triangles on a surface which has positive curvature have angles which add up to more than 180 degrees. On a flat surface, we all learned it already in like primary school, that the angles in a triangle are equal to 180 degrees. Now, a space with a negative curvature is one where triangles would have angles that are strictly less than 180 degrees. And that's one way of thinking about what it means for them to have negative curvature. So anti-de Sitter space is a space which is completely homogeneous. It's maximally symmetric. That means that every point in it is the same as any other point. It's related to it by a symmetry. And any orientation is the same as any other. So that's just like being on the surface of a sphere. A perfect sphere, I mean, every point is the same as any other point, and there is no way to define a preferred orientation. Anywhere is the same as anywhere else. So imagine the same kind of thing, like a sphere for positive curvature, but now we're imagining an object for negative curvature that's like that. If we were just talking about space and not time, then the description I just gave you would give you a hyperbolic space. Hyperbolic space is a homogeneous space with constant negative curvature. But if we're talking about both space and time, then that's like hyperbolic space, which includes both space and time, yes? That thing is anti-de Sitter space. So I just gave you a description of what anti-de Sitter space is in sort of tangible geometric terms. And so imagine our world is not anti-de Sitter space. When we draw triangles in our world, certainly they don't have angles that add up to less than 180 degrees. But you could imagine that what if we lived in such a world, yes? This would be some kind of a toy model for a theory of gravity. And the equations of motion for theory of gravity in anti-de Sitter space could be the same as our equations of motion. So locally, we could be talking about the same type of gravity. It's just the boundary conditions at infinity that are different from our world. So we're talking about gravity with anti-de Sitter boundary conditions. But it's still Einstein gravity. It's the gravity that we know, only at infinity we impose different boundary conditions on it. And for a reason which I don't have time to explain now, when we talk about anti-de Sitter space, it's natural to use a type of coordinates which make anti-de Sitter space look like a cylinder. And so the most common drawing of anti-de Sitter space is a cylinder. So here we have a cylinder on the left of the picture, and the vertical direction in the cylinder is time, whereas the horizontal slices of it, the cross sections of the cylinder, which here look like discs, but we could be in higher dimensions, then they wouldn't be discs, they would be balls. These are the spatial geometries, and the vertical direction is time. So what I just described to you is I invite you to think about a theory of gravity, which is just like ours, but at infinity, we impose different boundary conditions, and those boundary conditions are appropriate for a space-time with negative, not positive, but negative curvature, and that's anti-de Sitter space for us. And it's drawn as a cylinder. So that's a summary of what I said so far. Now, it's a miracle that we discovered. I mean, it's a physicist's miracle. Yes, it's a very exciting thing. Yes, that some 25 years ago, or even more, 28 years ago, people discovered, I was too young to discover that at the time, but Juan Maldacena in particular, and some other people, Edward Witten, and a few other people were instrumental in that discovery. People discovered that a gravity theory in anti-de Sitter space can be equivalently described by an ordinary field theory without gravity. It's a little bit of a special field theory called conformal field theory. What's a conformal field theory? Roughly speaking, a conformal field theory is a field theory without any scale. So when we talk about field theories that we know, yes, then I don't know if the Lagrangian for quantum electrodynamics or for the electroweak theory, all of these things have various scales which are associated with like the masses of the particles or with the coupling constants also run. But here we have to imagine a theory that has absolutely no scale at all. In fact, when we say conformal field theory, we have to add an additional requirement, which is technical, but I would like us to just ignore that technical requirement. For our purposes today, let's assume that the conformal field theory is just a field theory without scale, period. Okay. So the amazing discovery from 1997 is that you take this theory of gravity I talked about before, ordinary gravity with anti-de Sitter boundary conditions, and then you take a conformal field theory, and the amazing statement is that they are one and the same theory. You just have to know how to translate from one to the other. And this is called the ADS-CFT correspondence. ADS for ADS boundary conditions, anti-de Sitter, and CFT for conformal field theory. And one more amazing thing about it is that the ADS-CFT correspondence, in the correspondence, the anti-de Sitter space has one more dimension, and a conformal field theory has one less dimension than ADS space. So for that reason, we often call it a holographic duality. So what's a hologram? It's a two-dimensional rendition of a, excuse me, three-dimensional picture, right? So ADS-CFT works in the same way. The CFT contains all the same information as ADS, but it's a one less dimensional object. So it's like a two-dimensional, for example, a two-dimensional encoding of a three-dimensional picture. Yeah, you can imagine, if you imagine a hologram, the image you are viewing in 3 dimensions is like lives in ADS, and then the encoding of it on a two-dimensional surface is like the CFT. So that's the kind of relationship we have between ADS and CFT. And in terms of the cylinder that we talked about, ADS is a cylinder. ADS is a solid cylinder. It has the interior. The CFT is basically the empty cylinder. It's just the boundary of that cylinder. That boundary in proper terms, in terms of proper distance, is infinitely far away from the center of ADS, but it is it's what we call an asymptotic boundary. It's infinitely far away, but it is possible to define a boundary if you do a mathematical trick. I do not want to talk about it in any more detail. So far, what I have described to you is just a basic setup for where I am doing my work. I haven't told you anything about my work. I just told you about the setup and the context. Oh, and maybe I should say one more thing, which is that why is the ADS-CFT correspondence interesting? Well, it's a famous fact that we don't have a quantum theory of gravity that is complete, yes? So people have come up with various models like string theory or loop quantum gravity or dynamical triangulations or something. There are various ideas for how to define a quantum theory of gravity, but for various reasons, some of which are hard and some of which are easy to explain. The easy example to explain is that G Newton has the wrong kind of mass dimension, so it turns out to be relevant rather than irrelevant. Or if you do an RG flow, so if you go to a UV complete theory, the corrections become more, not less important. Or another way to say why quantum gravity is difficult is that we always have to write down like Schrödinger's equation on some background, but in a gravity theory, the background itself is the thing we're trying to describe. So there isn't a good way of describing what it means to have, for example, a linear superposition of different geometries, which you would have to have in a quantum theory of gravity. So for various reasons, quantum gravity is really difficult as a general statement. But the ADS-CFT correspondence is the one and only miraculous exception where we exactly have a quantum theory of gravity, and we know it completely. And why is that? It's because of the duality. Because every question about the quantum gravity with anti-de Sitter boundary conditions can be translated into some other question in conformal field theory. And conformal field theory we know so well that we can answer any question we want to, basically. And so because of the duality, we have this one very exceptional theory for which we actually have a quantum theory of gravity. Maybe it's not the only exception, but it's one of 2 or 3 that we currently know. So So that's the reason why ADS-CFT is exciting, because it's one of the only models we know of quantum gravity, and it's an extremely useful toy model, one in which we can calculate a lot of things exactly. And so that's why I'm studying the ADS-CFT correspondence, and many other people do it. And one professor here, I'm already blanking out on the name, I'm sorry, studies the CARE-CFT correspondence. I understand that's also a variant of the same duality. Okay, so are there any questions about what I said so far? I will pause for a few seconds and then I will continue if there are no questions.
Okay, I just want to make sure that the slide that you use is still the same. I mean,
Oh yeah, because I haven't started the actual slide. I'm just talking about what we have to know before we get to talk about the slides.
Because as a moderator, I just want to make sure you don't that the screen is not freezing out. So okay.
No, it's all good. It's all good.
Okay.
Sorry, so I apologize that I haven't prepared the slides for this part of the talk. But we will soon get to talk about the actual content of the slides. Okay, so I said so far what I said is that I introduced the ADS-CFT correspondence, and I told you that it's very exciting that we can translate any question in quantum gravity if I have ADS boundary conditions. I can translate any such question into a question in a conformal field theory. So that translation is called the holographic dictionary. Excuse me. And the holographic dictionary is the key thing that we have to know if ADS-CFT is going to be useful. We have to know how to take questions in gravity that we care about and how to translate them into questions about conformal field theory. If we know the translation, then we know how to answer any question. And so a lot of people study the holographic dictionary. They study the art of translating anti-de Sitter gravity questions into CFT field theory questions. That's a very important subject of research. And so today's talk is about one or two really such entries in the holographic dictionary. So two specific things that we have learned how to translate from ADS into the language of the CFT. And these are two things that I have discovered with my collaborators. And so that's the reason why I'm about to tell you about them. And one more thing that I want to say is that I have decided to give this specific talk, partly because I was hoping that people would have heard the talk from BRIN 2 days ago. So then this talk is kind of a or in many ways continues the thoughts that were developed there. But another thing is that I thought that rather than giving a completely broad overview, which I just summarized in words, I thought that maybe it's better if I talk about one problem in some degree of detail, so that if there is a student out there in the audience, so I'm not talking about the older professors here, but about the younger people in the audience there. But if there is a younger person in the audience who wants to do research in this thing, then maybe it's important to give a flavor of just what kinds of things we do. If I gave you a very broad overview, then you would not know what one research project really feels like. But this way you will get a sense of what a research project in my field actually feels like when you're doing it. Okay. Any questions or comments? So I'm about to start actually talking about the slides. Okay, so so far I told you that it's so far I told you that the ADS-CFT correspondence is useful and exciting, and I told you that it's very important to study how to translate questions about ADS into the CFT language. Now, there is one element of this holographic dictionary, one thing that relates ADS to CFT, which is so profoundly important that it underlies most of the things that we do now. And this is called the Ryuta-Kayanagi proposal. You can see a little bit of it on the slide where I say RT surfaces. RT is for Ryu Takayanagi. So what did Ryu and Takayanagi tell us? They told us that if you take a, so we now have to start talking about the cylinder here. Can people see when I move the mouse on the screen?
Yes, we can see.
Okay, very good. So this is a picture of ADS, and I told you that the vertical direction is time. So if I look at an equal time slice, so if I don't go in the vertical, but sort of look at one snapshot like this is what I have drawn on the right-hand side here. This is an equal time snapshot of this ADS spacetime. And I said that the CFT lives on the asymptotic boundary of ADS. So the solid cylinder is ADS. This is the interior of ADS at an instance of time, at one particular time. Whereas the boundary is the CFT. That's where we have the holographic description. So this circle here describes the holographic description of the state of quantum gravity at that particular instance of time. This is the one time slice, in other words, a Cauchy slice of the CFT. That's where the information about one particular time of the CFT resides. Okay. So what Ryu and Takayanagi told us is that suppose that I take this state of the conformal field theory that lives on this circle, and I divide that state into two pieces. One piece will be this interval, and the other piece is the complement of the interval. So loosely speaking, you can imagine that this interval is like my lab. That's where I will do experiments. Whereas the interior is like the rest of the CFT universe. It's the things that are outside of my lab, yes? So it's a famous fact that, well, in quantum mechanics, we have quantum entanglement. A conformal field theory is very much a quantum field theory. So we can ask the question, how much entanglement is there between my lab, between this interval that I have singled out, and the rest of the conformal field theory? That's a question in the conformal field theory that we can ask. Like, how much entanglement is there between one part of the conformal field theory and the rest of the conformal field theory? The amount of entanglement. A quantity that quantifies how much entanglement we have is called entanglement entropy. I mean, there are many quantities that do it, but the best quantity that captures how much entanglement we have, the one that's most commonly used and most useful, is called the von Neumann entropy, or people just call it entanglement entropy. And what Ryu and Takayanagi told us is that this entanglement entropy in a CFT, a measure of how much entanglement I have between here and the rest, when I translate it into the ADS language of gravity, it's equal to the area of a minimal surface that separates this part from that part of the CFT through the bulk. This is a really astonishing statement because, and I remind you that if entanglement is quantified by entanglement entropy, so this is naturally an entropic quantity. It's a type of entropy we're talking about. So this is a really astonishing statement because it says that minimal surfaces in an ADS, in this ADS CFT correspondence, which is so exciting to us, a minimal area in ADS is equal to the amount of entanglement in the CFT. So think about the world that we live in. Imagine that we actually lived in ADS, and think about all the gravitational phenomena, such as, you know, things falling and so on. Now, all of this we know after taking a class on Einstein's theory of relativity. We know that the description in terms of F equals ma and Newton's formula like F equals gmm over r squared, those formulas are just effective descriptions of a much more complete theory in which there aren't really forces. There are only curvature of spacetime. So spacetime curves, and that's what we see as gravity. Now, if a spacetime curves, think about what happens to minimal surfaces, surfaces that have which have globally the smallest area subject to some boundary conditions. If a spacetime curves, then a minimal surface is going to bend in some way, and it will become a little smaller or a little larger depending on the curvature. So you can imagine that if we knew everything about minimal surfaces, then maybe we would know all about the curvature of spacetime, and then we would know all about Newton's equations, all about gravitational phenomena that we experience in our daily life. But it's all in those minimal surfaces. And now Ryu and Takayanagi tell us that those minimal surfaces are really measures of entanglement in the CFT. And so when you put it together, the statement is that entanglement in the CFT is entirely responsible for gravity in anti-de Sitter space. And it's all because of this Ryu Takayanagi proposal, which says amount of entanglement equals a minimal area. So I hope that I have conveyed to you just how important.
Yeah, yes, question.
Yeah, there's a question.
Yeah. In that picture, how you define the singularities?
Oh, so this is in here when I started talking about the Ryu Takayanagi proposal as if the spacetime was static. If we have a singularity, then well, I guess we could have a time-like singularity, but for the most part, we imagine that a singularity is something that would hit in the future if we fall into a black hole. So typically we talk about space-like singularities. So then if you have a space-like singularity at a particular instance of time, then your spacetime is no longer static, yes? But here I have assumed that the spacetime is static. So to really answer your question, I would have to tell you about how the Ryu Takayanagi proposal is modified in the presence of non-trivial time dependence. Maybe it's best for me to not really answer that question, but if you're seriously interested, I can send a reference later about how the Ryu Takayanagi proposal is modified in the presence of time dependence.
Okay, thank you.
Okay, so far, so the thing that I just described to you is this picture. Here is like our lab. It's a CFT lab. So it's just part of a CFT, and it's entangled with the rest of the CFT. And the CFT makes a holographic description of this ADS space. And the idea is that the amount of entanglement between here and here is equal to the area of this surface, which is a minimal surface for ADS. This is the most important thing. This is the only thing that you have to know about the Ryu Takayanagi proposal. And it's the starting point for everything I have to say. Okay, so Ryu and Takayanagi proposed their thing in 2006. So we have known for almost 20 years this fact. But then I remember I said that in this game of trying to understand quantum gravity using ADS CFT as a toy model, the key thing is to know how to translate questions from one side to the other side. So Ryu and Takayanagi gave us a translation like that for one specific thing, which is they said, if you have a minimal surface, it computes the amount of entanglement in the CFT. Very good. But then you would say, what if I have a non-minimal surface? If I have a non-minimal surface in ADS, can I also compute its area in some way? And if so, how do I do it? And so that's the question that I will be talking about today. And the answer to that question is called differential entropy. And it's something that I was very lucky to discover along with some collaborators some years ago. So the problem that we have, and now I'm starting to talk about like my original research. The problem that we're facing is, imagine that you have, Ryu Takayanagi told us a statement about a minimal surface. What if I have a non-minimal surface? For example, it could be this red oval, yes? And we're asking, it's some like observable in ADS, the length, if you like. So here I will be working in ADS-free CFT2. That means that a spatial slice of ADS is two-dimensional. That means that if I draw a surface, it really is a one-dimensional curve. So we talk about lengths now. So a question that you can ask is, the length or the circumference of that thing, how do I compute it? It's something in ADS, which is a well-defined observable. How do I compute it in the CFT? Okay, so that's the question we have here. And so what I'm going to do now is just quote the answer for you. And this is the answer is called differential entropy. And this was discovered in 2013 and 2014, really 2014 by these collaborators of mine along with me. And let me just unpack a little bit what this formula says. So if I have this curve here, then I can try to relate it to the Ryu Takayanagi proposal, which is about minimal surfaces. So what I can do is I can try to look for a set of minimal surfaces like this one, which are just tangent to my curve. Okay. So it's just tangent to my curve. Now, this is one tangent minimal surface to my curve, but it's not the only one. There will be others like this and like that and like that. Each of them has one endpoint and another endpoint, two endpoints. The fact that this Ryuta-Kayanagi surface, this minimal surface, is tangent to my given curve imposes one condition on the, or one relationship between the left endpoint and the right endpoint of the curve. So we will call this condition u as a function of v. You give me a v, and I will give you a u such that the curve is just, the minimal surface is just tangent to my curve. So using this u of v gives us a way of encoding the information about that curve, which is not minimal, using curves which are minimal. And then we can use the Ryuta-Kayanagi proposal. So if you do that, and you want to compute the length of this curve, then it turns out that this formula is correct. You take an integral over this quantity v, over this variable v, and then the integrand is this partial derivative of s, where s is the entanglement entropy for this interval. So you see, the protagonist in this formula, the thing that lives in this formula, is really entanglement entropies. We're still talking about entanglement, but we're taking derivatives of that entanglement. And that's why we call it differential entropy. So normal entanglement would be, ordinarily entanglement would be quantified by entanglement entropy, but now we have to take derivatives of that entanglement entropy. So that's why we're talking about differential entropy. So the answer to the question, how to compute the length of this curve, is given by this object called differential entropy. It's an integral of the derivative of the entanglement entropy. Okay, and these are facts from 10 years ago. Now, I'm going to tell you some more about this formula because it's kind of exciting, which is that we can do something interesting with this formula. So far, I told you that we can do this integral, which computes the differential entropy. We can do this integral over all curves, and in the integral, we're substituting u equals uv. So this is an integral which only happens over geodesics which are, or minimal surfaces which are tangent to the curves. But here's what we can do. We can try to be a little more abstract about this and say, this integral is somehow living, or is set in a larger, higher dimensional context where I can form a new space, which is the space of all possible minimal surfaces, these Ryuta-Kayanagi surfaces that compute entanglement. This space is a two-dimensional space because every minimal curve has two endpoints, one left endpoint and one right endpoint. And so I have two things to vary if I want to describe to you a minimal surface, a Ryuta-Kayanagi surface. So imagine making a space in which every point here corresponds to one such minimal surface. One point is one surface. So for example, this minimal surface here, which has an endpoint u and an endpoint v, would be given by this point u comma v in this new space. We call this new space kinematic space. Then the integral of on the previous slide, it was an integral over all curves which are just tangent to my curve. So if I draw this function u of v, which tells me where the tangency happens, I will draw a locus of this kind in this kinematic space, the space of all possible minimal surfaces. But in fact, I don't just draw one such thing, I draw two of them, because when I say that a given minimal surface is characterized by u and v, it's not just the surface itself, it's an oriented surface. I know where the left endpoint is, this is u, and I know where the right endpoint is, which is v. And you can say, and by knowing that, I know that I'm talking about the entanglement entropy of this specific interval and no other. Well, you can say, what if I wanted to describe the complementary interval, this interval? Then u and v would exchange roles, yes? Then this u would become a new v, and this v would become a new, this u. We would exchange the role of a left endpoint and the right endpoint, yes? So really, if you just give me a minimal surface, you're really giving me 2 points in this space. One where we have endpoints u and v, and the other one which is reversed, which talks about the complementary intervals on the boundary, which is called v and u. And I'm really drawing two curves, the purple curve due to this assignment of U and V, and the green curve, which is the opposite assignment of U and V. Okay. And both of them, if I plug them into the differential entropy formula on the previous slide, will compute for me the same length. So I can do the following operation. I can say length is equal to half of the formula where I use U of V and half of the formula where I use the opposite orientation, V and U. And then I'm really doing an integral which goes this way and that way, and taking 1/2 of both of them in this kinematic space, the space of oriented minimal surfaces. But now I can do the following thing. Now I can say, oh, I have my integral covers the boundary of a compact region in this space. And so I can use Stokes' theorem, and Stokes' theorem will turn these one-dimensional integrals into a single two-dimensional integral over everything that happens in between these two curves. And what's in between these two curves? What's in between these two curves, before here, this was a locus where minimal surfaces were tangent to my curve. In between one type of tangency and the other type of tangency, I will have things that go right through the middle here, and they just intersect my curve. And so really the locus of integration in this formula is we're really integrating over all minimal surfaces which intersect the curve. So we have rewritten, so this formula is correct. Here I have a second derivative because I applied Stokes' theorem. So I applied an exterior derivative. And what I want to say is that in this formula, we have a very interesting thing. We say that length in anti-de Sitter space, so length in gravity as we observe it, if we are gravitational observers, is equal to this two-dimensional integral over all possible minimal surfaces that intersect my curve. So this it's a very interesting thing because we're not used to thinking of length as something which is built up of intersecting objects. Yes, like if I tell you what is the formula for the length of something, for example, the length of this piece of string. Yes, then you would say, oh, if I have a formula for this length for what this piece of string really does in space, then I could write down in calculus, we are taught, oh, just write down an integral. It's an integral of a length parameter of something like square root of 1 plus dy dx squared. That's a formula that we typically use for length, yes? So we're used to thinking that length is defined in terms of some calculus formula. But this is a completely different way of thinking about length. Length is a measure of how many things intersect the curve. And that's what we have here. And apparently, in the ADS CFT correspondence, the way in which we can compute lengths of arbitrary objects is really that way. So a person who first studied this way of thinking about length was called Crofton. This was an Irish mathematician, and he lived 150 years ago. But he only studied it in flat space. And so here, by working on the ADS CFT correspondence, we rediscovered a new version of his formula, which applies in anti-de Sitter space, because we're interested in quantum gravity in anti-de Sitter space. Okay, so the key take-home message from this slide is that length is given by an integral over intersecting minimal surfaces, and each minimal surface in turn computes the entanglement of some region in the dual conformal field theory. Okay, now this thing has the content of this slide. I hope it's kind of exciting. It certainly is exciting for me, but it has a problem. The problem is that we can only do this derivation if the space-time that we have here, this space-time, so this anti-de Sitter space, is topologically trivial, if there are no holes in there. What if there was like a hole in this space-time? We can say, why would I have a hole? You could have a hole because you might be describing a black hole in anti-de Sitter space. So what would happen if you had a black hole in anti-de Sitter space? Well, this is something that we are familiar with from talking about astronomy. So how do we know how do we detect the presence of some like massive object which is dark? Well, we see that there is light coming from it, from something behind it, but then we see that light from the same object comes to us in we see it in two different points in the sky. Why is that? Because two different light rays got bent coming to us, one this way and one that way. Yes, this is a common phenomenon in gravity, that light is in Einstein's gravity, light is bent by the presence of massive objects. So a massive object. So if we see the same object shining at us at two different points in the sky, then we know that there must be some massive thing in between us and that object. Okay, so here we have the same kind of phenomenon. We would have the same kind of phenomenon if we had a black hole here. If I happen to put a black hole in the middle of this picture, then these minimal surfaces wouldn't look like this. Instead, they would start rotating, being attracted by the black hole. So they could do something like this, or maybe even rotate around the black hole more than once and only then come back to the boundary. And so this is a problem for this derivation, because here we assume that between one type of tangent geodesics and another type of tangent geodesics, nothing interesting happens. But if I have a massive object, which I can circle multiple times, then this derivation would no longer be true. And so, here's a picture of the kind of thing that is the problem. I imagine that there's a black hole here, and now a minimal surface can do something like this, yes? And our derivation just cannot accommodate this circumstance. So a question that you can ask is there a Crofton-like formula, something that we talked about on the previous slide, but which would also apply in the presence of black holes? And the title of my talk, Two-Sided Crofton Formula and Two-Sided Differential Entropy, tells you that I was planning to give you an answer to that question. I was hoping to tell you about just how to derive this type of formula, but a formula that actually works even in the presence of black holes. So I won't really tell you about it because it's already 4:20. So I apologize that I won't say all that much more about it. But let me give you just what I'm going to do now in the next maybe 10 minutes as I'm closing the talk. I'm going to go through the slides, not explaining them in detail, but I'll just show them to you like pictures to give you a sense of what kinds of things we do, or what kinds of things my research group and I really do when we do our work. And so what happens as we answer this question is that we take this formula, and the first thing we do is that we try to discretize it. And then we discretize it, you get it to the following form. And then we recognize that, oh, this form, we have seen it. This form of this discretized version of that formula, which actually computes the length of a curve, we have seen it before when we studied a related but actually very different problem, which is what are the necessary, this formula involves entropies, right? So what happens is that we have seen the same kind of formula when we studied entropies, but with a different question. When we asked what kinds of values of entropies are okay for a CFT state to describe holographically an anti-de Sitter type geometry. And the content of my talk at BRIN on Tuesday was exactly that. I talked all about just these types of entropic conditions, which are necessary conditions for a state in a conformal field theory to be dual, to describe holographically a spacetime geometry such as an anti-de Sitter spacetime. So there are some necessary conditions that a set of entropies has to obey if the entropies can really be interpreted as areas. Otherwise, yeah, the Ryuta-Kainagi proposal in particular told us that we think of areas as entropies. That's okay, but you can ask the reverse question. Can I always think of any entropy as area? And the answer is no. There are necessary conditions before an entropy can be thought of as an area. It turns out that a discretization of this formula is something that we precisely see when we study that problem. It turns out that just this combination of entropies, which discretizes this formula, is something that naturally shows up in that other problem. What are the necessary conditions for a set of entropies to become areas? And so, so here I we see two different types of discretizations, and the point is that both of them show up in this problem of entropic inequalities, which are necessary conditions for entropies to be areas. Okay. So the plan that I would have followed in the rest of this talk is that I would say we have this is the sort of the overview of how this research is structured. We have a formula where length is equal to differential entropy. We know that this differential entropy is definitely bigger than a horizon area if there is a horizon. And it turns out that this thing is one of those entropic conditions for entropies to be areas. Now, when I discretize this, okay, if I use Stokes' theorem based on this formula, then I get this Crofton formula, which I said was so exciting. Length re-expressed in terms of intersecting objects. But I know that this does not work if I have a horizon. But we're thinking maybe we can take this expression and discretize it, and then maybe we can take inspiration from some other entropic conditions, such that if you undo the discretization, you will get a new formula like this one, which does apply in the presence of a horizon. And in fact, this is what happens what would have happened in the rest of this talk. And so it's a way in which entropic conditions on when entropies can be areas turns out to precisely determine for you how to write down this more general expression for area, which applies even in the presence of black holes. And so this is the kind of the overview of this research. Now, just to give you a flavor of how complicated it gets, these are those entropic conditions that are necessary for entropies to become areas. This is what was known about them like a year and a half ago. But then my students and I discovered a new set of inequalities. And the new set of inequalities look kind of like this. And then they are related. So now I'm just giving you an overview at the level of a cartoon. It turns out that these inequalities can be, okay, first of all, they cover many of the ones that we had discovered before, but more importantly, they turn out to be related to tessellations of compact two-dimensional manifolds. And it's important that these manifolds are two-dimensional. What turns out is that the two-sided Crofton formula that we look for, the one that works in the presence of black holes, whereas the previous formula didn't, turns out to be an integral over a continuous manifold, which is the kind of manifold that I described to you here. And so maybe I should leave it at that. There's a lot of stuff that I just kind of showed you. There is no way that, I apologize, there's no way that you could have absorbed all of it, but I hope to give you just a sense of the types of questions that I study. And if there is some student, I want to really stress it, if there is a student out there who is really interested in joining this type of research and wants to learn more about it, then please contact me, and then we can really get going and study this thing in detail together. So thank you very much, and I will go back to the overview slide. Thank you.
Okay, thank you, Prof. Bartek. It's very interesting talk, and yeah, I think we are all happy to see your handwriting here, because nowadays it's rare that the speaker put it on a piece of paper. So I think that's a kind of originality, which I think we should go back to, right? Back to the old days. I think that's good. And maybe for the students, before we go to the question and answer, I would like to give a brief introduction, because there are many layman students here who really want to know the basics of your research. And maybe I just give in Bahasa Indonesia a little bit summary of what you gave. So, jadi teman-teman, Prof. Bartek membicarakan terkait dengan gimana kita bisa membayangkan tiga dimensi, ya, gravity, solve gravity tiga dimensi yang namanya anti-de Sitter space ini menggunakan holographic theory, di mana kita bisa mempelajari tiga dimensi menggunakan permukaan dua dimensi yang dikenal sebagai conformal field theory, ya, yang mengkoneksi gravity yang belum kita ketahui sepenuhnya dengan quantum mechanics. Itu mungkin salah satu warisan dari Juan Maldacena, ya. Kemudian beliau ini menerapkan yang namanya differential entropy, ya, untuk membantu kita di dalam menghubungkan 3D space yang anti de Sitter itu dengan conformal field theory. Nah, keuntungan dari differential
Dan kalau saya boleh, saya tambah satu lagi. Yang sangat penting adalah sebenarnya istilah apa yang mencerminkan permukaan dalam anti de Sitter space dengan CFT. Maksudnya apa yang berada di CFT yang terkait dengan permukaan di ADS. Dan yang menarik adalah itu quantum entanglement. Biasanya kalau kita tanya sebenarnya apa yang kalau ada permukaan, surface area, apa itu bermaksud? Pasti nggak akan ada yang bilang, oh itu terkait dengan quantum entanglement. Tapi ternyata ya, jadi untuk saya paling menarik adalah itu sangat surprising, sangat mengagumkan bahwa surface areas itu kita sangat udah sangat familiar dengan surfaces ya. Misalnya yang ini itu juga suatu permukaan. Tapi kalau kita bertanya itu terkait dari apa? Dalam tingkat yang paling basic, semua permukaan sebenarnya itu dibuat dari quantum entanglement. Ini buat saya paling menarik. Sorry ya.
Ya, itu bagus sekali. Jadi artinya kita punya yang namanya quantum entanglement di surface itu yang ternyata selama ini mungkin tidak dikaji secara mendalam, tidak di-study secara mendalam, yang ternyata itu bisa nantinya mungkin menguak rahasia atau kode gravitasi gitu ya di anti de Sitter space ini. Nah, ini luar biasa, saya kira one of the biggest mystery in physics ya. We try to solve here, Prof. Bartek ya. Oke. Ya, teman-teman silakan untuk komentarnya. Ini sangat menarik. Mungkin dari audiens yang angkat tangan dulu ya. Ada yang mau bertanya? By the way, Prof. Bartek, you can put these images in AI, and then he make a latex presentation for you. Ya.
Oh gitu. Ya.
Yeah. So you just copy paste in AI, and then ask him to make latex code, and he will make the latex code. Beamer. Yeah. So you don't, yeah, just in case you need. Okay.
So, boleh saya bertanya kalau begitu,
Ya,
biar nanti
silakan, Pak
juga yang
Arya.
lain mulai.
Ya.
So, I'll just ask you in English then. Stupid question. I mean, I tried to learn this through Takanagi formula since long time, but thanks to your talk now, I start to more understand about it. So, does this statement applies to ADS safety in any dimensions?
Yeah,
ADS safety.
correct. Yes, this statement applies to ADS CFT in any dimension. Right.
Okay. So then interesting about the Crofton formula. So I assume that you have generalized the formula to curved space because Crofton found it in the flat space, right?
That's correct. Yes.
So interesting. Which comes first to you? The idea of interaction stuff, as you mentioned before, or after you see Crofton, perhaps you can apply it to anything in Ryu Takanagi.
That's an interesting question. So what happened that I was at a workshop in Aspen Center of Physics,
Right.
and I gave a talk about this formula, which is just the formula about the tangent geodesic. And that formula, my friends and I had discovered it without any sort of input from mathematicians. We just thought about it and we discovered it.
Okay.
And I was giving a talk about this. And in the audience was Michael Friedman. Michael Friedman is a mathematician who actually at some point won a Fields Medal, and he works a lot on quantum computing these days. But he was there, and then he just watched this talk, and he said, "Isn't your formula wrong? Because there should be a formula like that about intersecting geodesics and not about tangent geodesics." And then, I mean, he said that, and then 2 or 3 days later, we had all of this stuff because we realized that, well, obviously, tangency is the locus of tangency is the boundary of locus of intersection. So Stokes' theorem will immediately give us some formula about that, and with intersecting geodesics, and that's probably what he was talking about. The moment we had it, then we compared it with literature from before, and we realized that this thing has a name called Crofton and so on. And one other thing I want to say is that, because I didn't say this, but since there is a question, so thank you for giving me extra opportunity to talk about it. So this integrand is very interesting because this integrand has a special form. First of all, if you know complex analysis, then this looks like S is a Kähler potential for a Kähler manifold. But another thing to say is that if you expand this thing, this second derivative, and you discretize it again, then this quantity is guaranteed to be positive and or non-negative. And it's guaranteed to be non-negative by a theorem in quantum information theory called strong subadditivity of entanglement entropy. So what's interesting is that strong subadditivity of entanglement entropy, it has its own interpretations. It's all about like how much mutual information there is and how much it increases by the addition of some extra region or something like. Anyway, there's some interpretation of it. But in ADS, that quantity, which is so important in quantum information theory, tells us what is the measure with which we should be integrating geodesics. Minimal surfaces that intersect my curve. So it's very interesting because it says that the natural measure with which we should integrate geodesic is an information theoretic quantity that people have studied independently. So I think it just tells you that the structure is very rigid and everything is connected to everything else.
Oh, okay. Thank you.
Oh yeah, can I have a question?
Yes, please.
Please do.
Okay, thank you. Thank you, Bartek. I was also attending your talk yesterday. Yesterday in BRIN, but I couldn't grasp the line, the important line of your talk. I mean, just like Haryanto question. So, for example, ADS space, for example, if we consider, for example, Schwarzschild ADS, so this ADS, we could see that this ADS space is in the asymptotic limit of the Schwarzschild. So it seems that I don't know, this formula somehow only valid in a weak gravitational field. If we go to the strong region of gravity, for example, near horizon or near singularity region, is it also? Is it possible to generalize the result?
Yeah. So so here nothing in this talk relies on the like the gravitational field being strong or weak, or anything like that. I do want to say that at some point I said that I will be working with the ADS-free CFT2 correspondence. So ADS is always one higher dimension of CFT, but there will be like ADS-free CFT2, ADS-4 CFT3, ADS-5 CFT4, and so on. So I'm specifically talking about ADS-free CFT2. So this is a 2+1 dimensional theory of gravity, dual to a 1+1 dimensional conformal field theory. In that dimension, we don't really talk about the Schwarzschild black hole. We talk about what's called the BTZ black hole. BTZ is like the closest version analog of Schwarzschild, but that happens to work in 2+1 dimensional empty de Sitter space. So I just wanted to make a small correction that I wouldn't use the word Schwarzschild, but BTZ here. But for the BTZ black hole, everything here works perfectly. And in fact, the whole point of the part of the talk that I didn't give, or which I just kind of showed you very quickly, is that we had a formula that worked only without black holes, and now we know how to write down a formula that also works in the presence of black holes. The BTZ is the primary kind of black hole to which we want to apply it, and yes, it works there.
Okay, is it? So you mean that it is possible that it can be applied and generalized to other black holes in the future, not only this BC?
Well, we can yeah. So first we have the rotating BTZ black holes, and it applies there with some an appropriate version of it will apply there, and then we can also have we can like couple the black hole to some bulk fields, and it will also apply there. Yeah, it just applies without any restrictions, but except the restriction on dimension. So this is for 2 + 1 dimensional anti de Sitter space.
So maybe in the forum, if a student is interested to further deepen the application of your theory, this will be interesting. Okay, maybe Hadian, you can ask.
Yeah, Hadian had that question.
Hadian, please.
Ya, terima kasih. Mohon izin untuk bertanya dalam bahasa Indonesia, Pak.
Okay.
Kira-kira apakah non-minimal surface yang dihitung dengan differential entropy ini bisa mempelajari besaran-besaran lubang hitam seperti misalkan temperatur atau evaporating time yang dibahas 2 hari yang lalu, Pak?
So this curve is not so the curve that I'm talking about is just some curve that we imagine. So this is not it's not a horizon of any physical object. So I wouldn't really apply the same notions there. If we are very creative, then maybe we can talk about some kind of local temperature associated with the surface of that kind of curve. But because the curve is not homogeneous, not necessarily homogeneous, so we would have to imagine that the temperature varies with where I am on the curve, depending on the local curvature of the curve. But I tried to think about it in those terms a while ago, but I didn't really think it was very successful. So I don't really have a good answer to that question.
Okay.
Thank you very much.
Yeah, you wanna add something, Hadian?
Maybe follow-up questions. Is it possible?
Yeah.
So this red line here cannot penetrate to the interior.
Sorry, what's the question?
The red line here cannot penetrate to the interior of the black hole.
Oh, so in this formula that I started with, it doesn't. But then in the formula that I eventually derived, which I didn't really tell you about, then that more general formula, it does allow to, it has a lot of interesting properties that I didn't have time to tell you about. But yeah, it's a lot more powerful, and there you can go into the interior.
Oh, I see. Thank you very much.
So Hadian, are you graduate student or?
Oh yeah, I just graduated from IPB.
Yeah. Okay. So maybe you can contact Prof. Bartek after.
We have already been in contact with Hadian.
Okay. Okay.
Yeah.
So you already have behind the skin operations, comfort operations.
Yeah, Hadian even came to a workshop that I organized on Bali in November. So yes.
Yeah. I think it's good opportunity, Hadian. Yeah. If you really like this topic, yeah. Okay. Maybe just one. Is it? Do we still have time? You have to
Well,
check
to be honest, I actually have to go to the plane right now. So I think I have to say goodbye to everyone right now in like 1 minute.
Okay.
So yeah, let me just say thank you very much for listening to the talk. I am sorry that the talk was a little hard to absorb for everyone. I tried to strike a balance so that an interesting student like Hadian would benefit, but also people who have never thought about these things would also benefit. I don't know if I struck the right balance, but I tried. And thank you very much.
Thank you very much. Great talk.
Okay, thank you, Bartek. And before you go, we just want to tell you that we have a certificate of attendance for you. So just before you go, just 1 minute, let me share it. Yeah. Maybe Prof. Husin or Prof. Tony, you can present this.
Prof. Husin, maybe.
Yeah. Thank you, Pak Bartek, for your presentations. Very nice. And we do enjoy your presentations. You want to fly to?
I'm flying to Solo in
Okay.
in just very, very, very soon. Yeah.
Yeah. Have safe flight, Pak Bartek.
Thank you very much.
Thank you very much.
Many thanks to everyone.
Very much.
And let us all keep in touch, especially with the young students who are interested in research. I very much welcome that. Yes.
Okay, thank you. And excuse me, this is the certificate of appreciation for you.
How do I see it?
You cannot see it?
Is it something that can be sent by email or?
Yes, yes, of course. I will
Then
send it to
please
you.
send it by email or by WhatsApp.
Yeah, we
Either
will
one.
send it now by WhatsApp.
Oh,
Right.
great. Many thanks and goodbye, everyone. Thank you.
Goodbye.
Thank you
Bye-bye.
very
Bye.
much. Have a safe
Bye.
flight.
Thank
Thank
you.
you.
Thank you.
Thank you,
Terima
Pak
kasih semua ya.
Goodbye.
Ladies and gentlemen, it was an interesting talk, and let's hope that you can join us in the next physics talk with another speaker. Thank you all the participants, Pak Haryanto, Prof. Tony, Prof. Husin, ada Pak Bobby tadi, dan teman-teman yang lain. Nggak bisa saya sebutkan satu-satu. Mudah-mudahan Physics Talk ini akan terus bergelora dan menjadi salah satu start dari kemajuan fisika di Indonesia. Terima kasih
Amin.
semuanya.
Terima kasih
Amin.
Pak Dodi, Pak
Terima
Husin,
kasih,
Pak
Pak
Tony,
Rianto.
Pak Bobi yang
Oke,
lain.
terima kasih
Iya.
semuanya.
Sore.
Terima kasih.
Thank you, Pak.
Terima kasih.